Okay, hello everyone. Welcome to the algebra session. I am Tomoyuki Arakawa from RIMS Kyoto University. It's my great pleasure to introduce the joint lecture by Pierre-Emmanuel Caprace, who is a professor at UC Leuven, and George Willis, who is a professor at the University of Newcastle. The title of the talk is A Totally Disconnected Invitation to Locally Compact Groups. Unfortunately, we don't have time for questions, but you can ask questions on the Discord platform. So please.
Well, thank you for that introduction. Pierre-Emmanuel and I thank the IMU for the honor of the invitation to speak at this International Congress. And we also thank the organizers for the work they've done in bringing us all together for this Congress under difficult circumstances. We'd also like to thank our collaborators whose work has contributed to this talk, and some of them are listed on the slide. You see there. Now I'll give a short introduction before handing over to Pierre-Emmanuel to say the next part of the talk. So despite the title, this talk is not totally disconnected. It does come in two components, and I will deliver one component and Pierre-Emmanuel the other. The subject of totally disconnected locally compact groups forms part of the theory of general theory of locally compact groups, and that theory has two main origins. The first was Hilbert's fifth problem, asking whether it's necessary to assume that the group operations are analytic in the definition of Lie groups. And the second is from abstract harmonic analysis. The theorems of Haar and Weil show that the locally compact groups are precisely that class of groups for which there is a left invariant measure, translation invariant measure, and that's exactly what's needed in order to extend harmonic analysis from the circle or the real line to a larger class of groups. Now, every locally compact group divides into two parts. The connected component of the identity, which is denoted GO, is a closed normal subgroup, and the quotient by that closed normal subgroup is a totally disconnected locally compact group. And GO is a projective limit of connected Lie groups, and so any connected locally compact group is a projective limit of connected Lie groups, and the solution of Hilbert's fifth problem can be used to answer questions about the structure of such groups. The main fundamental theorem about totally disconnected groups is that of Van Dantzig from the 1930s. He showed that every totally disconnected locally compact group has a base of neighborhoods of the identity consisting of compact open subgroups. And that theorem is the base of a lot of the results that we're going to be talking about today. Now, here are some examples of classes of tdle groups that you might know. The first two classes there, the discrete groups and the profinite groups, are not we don't say anything directly about the structure of those, because the interest of this talk is in the interaction between the topology and the group structure. Then you'll see there are various classes that arise mainly in algebraic situations. We are not going to assume that you know anything about these any particular ones of these groups, except some of them will be mentioned in examples. The very last class there, the isometry groups of connected locally finite graphs. All such isometry groups are tdle, and it may be seen that the class of compactly generated tdle groups is more or less coextensive with the isometry groups of these connected locally finite graphs. We don't know how close this list is to being exhaustive. There could be a whole other classes of groups, tdle groups, that we don't know about. Now, Pierre-Emmanuel will tell you something about the decomposition theory for these groups.
Thank you, George. And indeed, the first chapter I would like to discuss with you is what we call decomposition theory. So decomposition theory involves the tools we have to decompose the algebraic structure of a given group into simpler pieces. So the underlying question can be formulated in that way. In what ways does a given group decompose into simple pieces? Of course, the word simple has a special meaning in group theory that I will briefly recall. A group is called simple if it's a non-trivial group, but its only normal subgroups are the two trivial ones. An equally important but formally weaker notion is that of characteristically simple groups. And these are the non-trivial groups whose only subgroups that are invariant under all automorphisms are the trivial ones. An example of a characteristically simple group can always be constructed in the following way. You just start with any simple group S, and then you take the direct product of two copies of S. This is always characteristically simple, but obviously it's not a simple group. In order to formalize decomposition theory, we consider finite ascending chains of subgroups in a group G, as shown on the slide. If all groups appearing in that sequence are normal subgroups of G, we call it a normal series, whereas if each term in the series, is normal in the next one, then we call it a subnormal series. Now, not all series of that form are equally interesting. The case of interest is when two consecutive terms in a series are such that no extra term can be inserted in between in a non-trivial way. So if this happens for two terms m and n in a subnormal series, then the subquotient n over m is called a composition factor of G. And it's not too difficult to show that every composition factor is always a simple group. Similarly, if you have a similar situation in a normal series, so two consecutive terms that are distinct and that are such that no extra normal subgroup of G is sandwiched between m and n in a non-trivial way, then the quotient n over m is called a chief factor of G. And such a chief factor is always characteristically simple. Now, with these terms at hand, we can define the notions of composition series and chief series. These are respectively the subnormal series involving only composition factors and the normal series involving only chief factors. Just to give an example of this, I put on the slide a chief series, for the group G, which is the semi-direct product of k squared with SL2k in its canonical action. And you have here a series with 4 distinct terms. It's a chief series, but not a composition series for that group G. An iconic example of decomposition theory is afforded by the classical theorem of Jordan-Hölder, and that holds for all finite groups. As soon as we allow infinite groups, it turns out that the existence of chief or composition series fails in general, and this happens for groups as elementary as the infinite cyclic group Z. That group does have composition factors or chief factors, but it fails to have any finite chief or composition series. And this is also the case for some non-abelian groups like the matrix group SL3Z. In the case of Lie groups, there is a very good decomposition theory on the Lie algebra level. And this can be lifted on the group level via the Lie correspondence. But there is an important point when doing this lift. So it's the fact that on the Lie group level, the discrete factors that may occur when decomposing the group will not be seen by the Lie correspondence. Indeed, discrete groups are zero-dimensional Lie groups. And this unavoidable matter of fact will again become manifest in the case of totally disconnected locally compact groups that I will now start discussing. So let's consider a group G that's totally disconnected and locally compact. So the normal subgroups that will appear in my discussion will implicitly be assumed to be closed, although I will not repeat the term closed each time. And here is an important and very nice theorem due to Colin Reed and Philip Wesolek. It concerns the tdle groups that are compactly generated. So by definition, this means G as a generating set that is compact. And for any such tdle group, there is always a finite ascending chain of closed normal subgroups, such that every quotient obtained by taking a term in the series and dividing out by the previous term, such a subquotient is always either a discrete group or a compact, hence profinite group, or a chief factor of G. Well, this theorem applies certainly to discrete groups like the infinite cyclic group Z. It's not excluded from the hypothesis, but of course the conclusion is not very meaningful, and one could very well take the trivial series of length 1. In that case, it satisfies the conclusion. If we consider again the semi-direct product we saw before, but this time over the field of p-adic numbers, then we obtain a non-trivial normal series here with 3 factors, and 2 of these factors are neither discrete nor compact, which shows that chief factors indeed occur in general. A key feature of this theorem, which is also somewhat surprising, is the finiteness statement, the fact that these series appearing here are indeed finite. This is related to the hypothesis that the group G is compactly generated, and is related to the fact that George alluded to in the introduction, that such groups are capable of acting vertex transitively on connected and locally finite graphs. A natural question about the theorem is whether the multiset of isomorphism classes of chief factors provide an invariant, a canonical invariant of the group G, which is independent of the specific choice of a given series, as it is the case for finite groups. It turns out that this uniqueness statement fails in general here, and this is related to the failure of the first isomorphism theorem for topological groups. However, there is a soft form of uniqueness that one can recover here, and that requires replacing the isomorphism relation by a slightly coarser relation. So the key message that one can remember from the statement is that indeed the building blocks of all compactly generated tdle groups are provided by the discrete groups, the compact groups, and the characteristically simple groups. The statement of the theorem I showed you is also provides motivation for several further research directions, and I will mention 2 of them. The first one is the study of the so-called elementary tdle groups that was initiated by Philip Wesolek. And this is the class of tdle groups that are exclusively composed out of discrete and compact groups. It turns out one can build indeed a theory for those groups. So one of the important ingredients of that theory is an ordinal value rank function that measures the complexity of those groups, and that can be fruitfully used for transfinite induction arguments. Another research direction that's obviously motivated by the theorem is the study of the characteristically simple groups, the chief factors. And this was initiated by Reed and Wesolek, and they came up with a typology of chief factors. They showed that there are only a handful of types of chief factors depending on the structure of their poset of closed normal subgroups. This poset can have a very complicated structure, and moreover, the ambient group G the conjugation action of the ambient group G permutes the elements of that poset, and that action can be very mixy. Despite these advances, it's fair to say, I think, that the chief factors remain mysterious in general, There is one case that's more favorable, is when the chief factor is itself a compactly generated group. Indeed, in that case, it is subject to a description that was known some time before. It's the following theorem. It says that if a characteristically simple tdle group is compactly generated, then it's not far from being a direct product of copies of a simple group. More precisely, if that group G is neither discrete nor compact, then there is always a non-discrete, compactly generated and simple tdle group S, and some integer n, such that the direct product of n copies of S embeds as a dense normal subgroup of G in such a way that the image of each simple factor S is a closed normal subgroup of G. So what we can remember from that statement is that it provides a way for us to pass from characteristically simple groups to simple groups. And I will take this as an excuse to move on to my next subject, which is indeed a discussion of some aspects of the simple tdle groups. Let me start this section by quoting a sentence that is due to Élie Cartan. So Cartan wrote once that it is a kind of historical law that the general properties of the simple groups have been verified first in the various groups, and afterward one has sought and found general explanations that do not require the examination of special cases. Although it's quite obvious that Cartan had the simple Lie groups in mind when he wrote that sentence, what I hope to illustrate with this section is that Cartan's historical law might as well apply to the class of non-discrete, compactly generated and simple tdle groups. That class includes many very important examples. The most notable ones are the simple algebraic groups over local fields. But the class also includes a very long and scattered list of nonlinear examples that all have some kind of a geometric flavor. And I will shortly come back to one of these, which is the isometric groups of a regular locally finite tree. Before doing so, I would like to step back and ask the following questions. So if I want to collect samples of simple groups in nature, where should I look for? And let's consider that question without imposing any locally compact group topology at the moment. An empirical observation that's verified by many examples is that very homogeneous mathematical structures tend to have an almost simple automorphism group. There are examples illustrating this coming from set theory, from linear algebra, from geometry, dynamics, and analysis, as shown on the slide. None of these groups actually happen to be simple in its own, but in each case, there is a canonical normal subgroup or quotient group that happens to be simple. The actual proof of simplicity usually being non-trivial. This is the reason why there is in each case one or several names attached to the proof of simplicity. One feature of some examples that we'd like to emphasize concerns the case of the homeomorphism group of a closed manifold. So in that case, the proof of simplicity combines the use of two ingredients that are properties of the action. The first one, I call it the compressible dynamics. And this means the existence of a non-empty open set O that can be compressed under the group action into every other non-empty set, open set U. The other feature is what we call a micro-supported action, is the fact that each time I consider a non-empty open set U, I can always find a non-trivial element of G that fixes every point outside of U. So the support of G is a subset of U. Once you have any homeomorphism group of a Hausdorff topological space that combines these two properties, then the normal subgroup structure of G is very restricted. More precisely, G has a unique smallest non-trivial normal subgroup S, and moreover, one can show that the S action on X is micro-supported. So if you happen to know in addition that the S action has compressible dynamics, then this argument can be bootstrapped and you obtain the conclusion that S was actually a simple group. And an example illustrating this can be found in the work of David Epstein on diffeomorphism groups of manifolds. So the key message here is that the combination of compressible dynamics and a micro-supported action naturally gives rise to almost simple groups. And the examples discussed so far were not locally compact groups in any natural way, but there is one more example that should be mentioned and that does carry a locally compact group topology, and it is the full isometry group of the D-regular locally finite tree. So one example is pictured here, it's the case D equals 3. So for those groups, the structure was studied by Jacques Titz, and he showed that this isometry group has a simple subgroup of index 2. The locally compact topology here is simply the topology of pointwise convergence for the action on the vertex set. Another property of this example that I would like to emphasize is the fact that these groups are rather big. So if you select any edge in the tree, you can always find non-trivial automorphisms of the tree that fix pointwise every vertex that's strictly on one side of that edge, and that permutes non-trivially the other vertices. So this can be done with any edge of the tree. And in that way, so this witnesses the fact that the action of that isometry group on a natural compact space, which is the set of ends of the tree, that action is again an example of a micro-supported action. Moreover, the hyperbolicity features of the tree allow us to show that this action has also a compressible dynamics. So Titz's work on that example was actually a source of inspiration for numerous other examples and constructions of simple tdle groups. But instead of describing them, I will now present the main result for that section, which is a statement that concerns all the compactly generated non-discrete simple tdle groups. So each time such a group has a micro-supported action on a compact space X, it turns out that the G action inherits extra features. The first one is that the action is minimal, meaning that all its orbits are dense. And then the action has dynamical features. The first one is that it's a strongly proximal action, meaning that every probability measure on X can be compressed under the group action to a point measure. And finally, the action has a compressible open set. It has compressible dynamics in the sense I defined before. That statement, I will not go into the proof, but one feature of the proof is that the micro-supported actions of the group G happen to be encoded in the algebraic structure of G via a local invariant that we came up with, and that's the centralizer lattice. So the key message out of this theorem is that we show that for non-discrete compactly generated tdle groups, the algebraic condition of simplicity combined with the micro-supported action gives rise to a dynamical conclusion, namely the occurrence of these compressible dynamics. This fact has various applications, and I will have the time only to discuss one of them. It concerns the notion of amenability. A locally compact group is amenable by definition if each time it acts on a compact space by homeomorphisms, there must be a G-invariant probability measure. Amenable groups occur naturally in representation theory, in ergodic theory, in operator algebras, among others. It's really a fundamental notion, and there is a long history of problems and results trying to relate the amenability of a group G to its algebraic structure. And a problem illustrating this is written on the slide, is the question whether a compactly durated, non-discrete, simple TDLC group can be amenable. And as a corollary of the theorem, we can answer this problem in the negative, provided the group G in question admits a micro-supported action on a compact space with at least 2 points. This is not quite the end of the story, in the sense that there are simple groups in my class, namely simple algebraic groups over local fields that are known to be non-amenable, but do not admit any micro-supported actions whatsoever. And another important remark is that the fact that the non-discreteness hypothesis is absolutely essential. Indeed, it was a very important advance in the past 10 years in the work of Yushchenko-Mono and Nekrashevich, who came up with the construction of the first examples of finitely generated infinite simple discrete groups that are amenable. Their groups arise in Cantor dynamics, more precisely, by their very construction. Their groups have a micro-supported action on the Cantor space. But that action has no compressible dynamics because the groups are amenable. And you see from that example that there is a very sharp contrast between the situation of discrete groups and the situation of non-discrete groups. Indeed, for non-discrete groups, the interaction of the topology with the algebra happens to have a very strong dynamical consequences, as these results aim to show. So I will not have the time to discuss further applications, so I stop here and leave it to George to continue the talk from this point.
Thank you, Pierre-Emmanuel. Pierre-Emmanuel mentioned that not all TDLC groups are linear. And what that means is that unlike the case of connected groups, we don't have methods of linear algebra available to help us to understand the structure of general TDLC groups. Scale methods that I'm going to talk about are to some extent a substitute for these linear algebra methods. The scale itself is defined in terms of the action of automorphisms on compact open subgroups. So suppose that we have some automorphism alpha and a compact open subgroup U, such as is guaranteed to exist by Van Danzig's theorem, then alpha of U is compact, and the intersection of the image of U under alpha with U is an open subgroup of that compact group. And so the index of that intersection in alpha of U is finite, some positive integer. The scale then is the minimum of these integers, indices of all compact open subgroups. And the subgroup U is minimizing if the scale is realized at U. The connection with linear algebra and eigenvalues can be seen in the formula for the scale in the case when G is a Lie group over a local field. So if we take AI to be the eigenvalues of the representation of this automorphism on the Lie algebra, now these are eigenvalues in some field extension of the field, then the scale is the product of the absolute values of those eigenvalues that are greater than or equal to 1. So in the case of the p-adic numbers, this is some power of p. For another example, which is not linear, if G is the isometry group of the tree, as discussed by Pierre-Emmanuel, and we have some inner automorphism induced by X, then the scale can be seen in terms of the action of X on the tree, and this is something that was worked out in the paper by Jacques Titz that Pierre-Emmanuel mentioned. If X has finite orbits, then the scale is equal to 1. If X has infinite orbits, then it is in fact a translation along some axis, And the scale is Q, which is one less than the regular valency of the tree, to the power D, where D is the translation distance. And it may be seen that the minimizing subgroups are associated with the axis. So that description of the automorphism of the isometry X is very closely related to the scale and minimizing subgroups. In applications of these ideas, it's often important to have a structure theorem for the minimizing subgroups, and that's what I wish to describe next. So we have our automorphism alpha and compact open subgroup, and define certain subgroups of U. So U plus is the intersection of all the images of U under non-negative powers of alpha, and U minus is defined similarly. Then U is minimizing for alpha if and only if U is the product of the subgroups U plus and U minus, and if the union over all powers of alpha of U plus is closed. Now, this union is automatically a subgroup. The condition here is that it should be a closed subgroup. If U satisfies these conditions, then the scale is the index of U plus in alpha of U plus. So the scale is the factor by which alpha scales up U plus. The compact open subgroup U satisfying these two conditions, TA and TB, satisfied by the minimizing subgroups. Any subgroup satisfying those is said to be tidy for alpha, and TA stands for tidy above and TB for tidy below, and these names are meant to indicate some intuition behind the proof of this theorem. The theorem can also be described in more dynamical terms rather than the algebraic ones, as it was stated. So here we have a picture of U satisfying TA. So this is meant to show that U is the product of U minus and U plus. And I now want to illustrate the tidiness below condition TB in the case where the scale of alpha is 3 and the scale of alpha inverse is 2. That means that in this picture, as we apply alpha, we shrink in the vertical direction by a factor of 2, and we expand in the horizontal direction by a factor of 3. And I want to illustrate what happens as we iterate alpha, starting with the pre-image of U under alpha, and we'll follow the orbit of the points shown here in various colors. So if we apply alpha to alpha inverse of U, we come back to U, and the points are mapped as follows. And now let's just repeat a couple more times, and we see that these points are moved as shown. Then, so summarizing, we have the subgroup U and these orbits, and there are several behaviors we see here. First of all, the black orbit misses U entirely. The green and the red orbit enter U and then leave, and just do so once. The orange orbit starts in U plus and then leaves U, and the blue orbit enters at U minus and then stays in U. Now, the condition, the tidiness below condition TB, is equivalent to the statement that when U is tidy, any such orbit can leave U at most once. Once it leaves, it never returns, and that's what's indicated in these in this picture. Now, we saw the blue orbit there, U minus. We were shrinking in that vertical direction. That's not meant to indicate that if we're in the blue orbit, the orbit converges to the identity. That's actually a stronger statement. The contraction group for the automorphism alpha is the set of all elements, such as X, such that when we iterate alpha, the images converge the identity. And that's contained in the subgroup U double minus defined here, which is the dilation of U minus under all powers of alpha. So this is a closed subgroup, just as U double plus was closed if U is tidy. But the containment can be strict, and so the contraction group is contained in U double minus, but the containment can be strict. And the relationship is shown in this theorem. So we suppose that U is tidy for alpha, and we'll define U sub 0, to be the intersection of all images of U under powers of alpha. Now that's equal to the intersection of U plus and U minus. Then this closed subgroup U double minus is equal to the product of U0 and the contraction group. So in particular, if U double minus is not compact, then the contraction group is not trivial. And not only that, but the closure of the contraction group is stable under alpha, and we can evaluate the scale by evaluating the module, the scale of alpha inverse, I should say, by evaluating the module of alpha inverse when it's restricted either to U double minus or to the closure of the contraction group. So as I mentioned before, this implies that if the scale of alpha inverse is strictly bigger than 1, then the contraction group is not trivial, and not only that, it's not pre-compact. It's not immediately obvious that the contraction group is non-trivial, but it follows from this theorem. Another observation to be made here is that every closed subgroup of the group G is unimodular, and this is sometimes called property R. Every closed subgroup is unimodular if and only if G is uniscalar, which means that the scale of every inner automorphism is equal to 1. Now, I'll mention briefly a couple of applications of these ideas of the scale and the tidy subgroups. I won't perhaps read through all of these statements in detail, but the theorem of Carl Hoffman and Arun Mukherjee here, mentioned here, is really the origin of the idea of the scale and tidy subgroups. The idea of a tidy subgroup emerged in the proof of a conjecture that was made by Hoffman and Mukherjee about tdle groups. So the theorem, as stated here, follows once their conjecture is proved, and their conjecture, which said that every tdle group is neat, which is something they had defined. If that is true, then the theorem, as stated here, follows, and the proof that that conjecture is true uses the idea of a tidy subgroup. There's also a theorem there about ergodic actions of automorphisms. This is what's stated here is a tdle case of a conjecture made by Helmholtz, that if a group has an ergodic automorphism, then it is compact. The connected case had been proved much earlier using approximation by Lie groups. I should perhaps mention Hoffman and Mukherjee proved the connected case of their theorem, but using approximation by Lie groups as well. Now I want to come to the next topic, which is extending the idea of scale and tidy subgroups to more than one automorphism. And the key definition here is the notion of a flat group of automorphisms. And a group is flat if it has a compact open subgroup that's minimizing for every automorphism in that group H. And the uniscalar subgroup of H is denoted by H sub U. That's the set of all elements of H that stabilize the tidy subgroup U. These ideas, I should say, are motivated by the analogy between linear algebra and the scale, because it's known that commuting linear transformations can be simultaneously triangularized, and there's also a converse statement, and we'll see a similar thing here. So, for example, every cyclic group is flat. If we take G to be the n-dimensional vector group over the p-adic numbers and H the group of diagonal matrices, they're acting on naturally on that vector space, then that is flat, and the subgroup of p-adic integers is tidy or minimizing. And for another example, if we take G to be SLN of the p-adic numbers and H the group of conjugations by diagonal elements now, then the Iwahori subgroup SLN of the p-adic integers is minimizing for H. Now, the structure of flat groups can be described in terms of roots. And for this, I wish to define, first of all, the subgroup U sub H0, which is the intersection of all images of U under elements alpha in H. Then a root of the flat group H is a surjective homomorphism from H to the integers, such that the subgroup U rho, which is the intersection of all images of U under not all our elements of H now, but only those where rho of alpha is greater than or equal to 0. If that subgroup is strictly greater than U sub H0, then rho is a root. And we'll denote the set of roots by capital phi. In the examples, the roots of the H in the, well, perhaps I'll speed up a little bit and just leave you to read those, but the roots can be defined in terms of valuations of the H in the flat groups. Now, flat groups and the subgroups tidy for them can be described as by the following theorem. If we so we suppose we have some flat group and that U is minimizing for H, then HU, the uniscalar subgroup, is the intersection of all the kernels of the roots. So in particular, if H itself is not uniscalar, there exist non-trivial roots. The quotient H by the uniscalar subgroup is a free abelian group. The roots can be ordered so that U is the product of the subgroups U sub rho. For each row, we can form the dilation of U sub rho by applying all alpha in H. That's a closed and H stable subgroup. And there is an integer S sub rho such that the module or the modular function defined on the restriction of H to U sub rho tilde is S sub rho to the root applied to alpha. That's for every alpha in H. In the examples, these integers S sub rho are equal to P. So the particular point here is that flat groups are abelian modulo the uniscalar subgroup. Conversely, we can there's this criterion for certain groups to be flat. If H is flat, H is flat if it's finitely generated and nilpotent, in particular if it is abelian. And it's virtually flat, which means that it has a finite index flat subgroup if it is polycyclic. Now, these ideas can be used to prove large part of a conjecture by Margulis and Zimmer about commensurated subgroups of certain arithmetic groups. The connection with TDLC groups comes about because the commensurated subgroups can be topologized to form a TDLC group. I'll finish there, but I'll just say that the results we presented here are only a selection of what is known, and a more complete statement can be seen in the article that we have contributed to the proceedings. Thank you.
Thank you very much for the nice lecture. So I think it's time to finish. So